The vast expanse of our universe, the seemingly infinite celestial landscape, continues to puzzle even the brightest minds nearly a century after we first grappled with its famous expansion. Questions like what set it in motion, why it continues to expand, and how we can even observe this phenomenon still baffle us. The enigma of the universe's expansion, once the brainchild of Soviet scientist Alexander Friedman, is something that has fascinated researchers ever since. Early pioneers like Henrietta Leavitt and Vesto Slipher paved the way for future researchers, allowing us to probe the depths of our cosmos. The 20th century bore witness to our attempts to measure the ever-elusive parameters of cosmic expansion. We've contended with concepts like big crunches and big freezes, and even found ourselves bewildered by unexpected acceleration. Imagine that, an accelerating universe? It's almost like the universe has a mind of its own. But then arises the concept of dark energy, a phenomenon that remains as elusive as the dark side of the moon. This mysterious force is driving our universe's expansion, and yet, we still grapple with its true nature. But hold on to your seats, because the real question, the real curiosity lies in. You'll have to stick around for that. Hey there, curiosity explorers. Ready for another dive into the unknown? I'm here with the wonderful Sonia, bringing you another intriguing episode of Curiosity Wonderland.
What's up, everybody? Excited to unravel today's mystery with you all.
And folks, we're so grateful for your support. Remember to subscribe to the channel, drop your comments, and share our podcast with your fellow curiosity explorers. Let's continue this journey of discovery together. Now, Philip G., a curious father, raises some interesting points on this topic. Like many of us, he's trying to make sense of this whole expanding universe thing. He's puzzled about the role of the Hubble constant in the expansion of space, asking if it's not accelerating, then why do we say it is? And if it is accelerating, is it because the Hubble constant is increasing? These are great questions, and while they may seem complex, we can gain understanding by taking it one step at a time.
Hang on a sec. Before we dive into Philip's question, can we talk about the Hubble constant for a moment? I've always been a bit foggy on that. Isn't it something to do with the rate at which the universe is expanding?
Absolutely. The Hubble constant is a measure of the current rate of expansion of the universe. Essentially, it tells us how fast the universe is expanding right now. However, despite its name, the Hubble constant isn't really constant over time.
So, it's more like the Hubble variable then, huh? But if the Hubble constant, or should I say variable, is dropping over time, how come we say the expansion of the universe is accelerating?
That's the crux of it all, isn't it? It's a bit like saying a car is accelerating, even though its speed is decreasing. The key lies with the concept of recession speed, the rate at which objects within the universe are moving apart. While the overall rate of expansion might be decreasing, the recession speed of individual objects within the universe is increasing. It's a bit counterintuitive, but that's cosmology for you.
Wow, so it's not so much that the entire universe is picking up speed, but rather that everything within it is moving away from everything else at a quicker rate. That's some food for thought.
Let's wind back the clock to just over a century ago. Einstein had just published his theory of general relativity, and it had been validated by the bending and deflecting of light during a well-measured solar eclipse.
That's the same theory that gave us black holes and gravitational waves, right?
Yes, indeed. Now, imagine you're a cosmologist in this exciting era. You want to apply Einstein's equations to the entire universe.
So, we're talking about the work of Alexander Friedman now?
Yes, the Soviet scientist himself. He figured that the universe must be uniformly filled with matter, radiation, and other types of energy.
Okay, and these assumptions led him to, what did we call them, the Friedman equations?
Exactly. These equations have been the cornerstone of physical cosmology for over a century. They tell us that a universe like ours can't be both static and stable, it must either expand or contract.
And this is where the idea of an expanding universe comes from?
Yes, and the rate of that expansion is determined by the combination of energy densities in the universe and its spatial curvature.
So, everything we know about the expanding universe essentially comes from these equations?
Well, the equations kicked things off, but then observation stepped in. The evidence for cosmic expansion began with Henrietta Leavitt's discovery of the period luminosity relation for Cepheid variable stars.
And those are the stars that change in brightness over time, right?
Yes, and by measuring how long it takes one of these stars to go from bright to faint to bright again, we can figure out how bright it is. And from there, we can determine how far away it is. These measurements confirmed that the universe is indeed expanding. As we delve further into the history of our expanding universe, it brings to mind a recent event. A few months ago, I had the opportunity to visit the Mount Wilson Observatory where Edwin Hubble, along with his assistant Milton Humason, took the measurements that confirmed the extragalactic nature of the nebulae.
Oh, that's a funny coincidence. Just last week, I was reading about Vesto Slipher, who discovered and measured the spectral line shifts of these nebulae. It's fascinating to think that they were moving thousands of kilometers per second relative to us.
Absolutely, and the majority were redshifted, which suggests they were moving away from us. It was Hubble's measurements, combined with Slipher's, that led to the revelation of the universe's expansion. When they put the distances of these objects alongside how quickly they seemed to be receding from us on a graph, it was clear. The universe was expanding, just as Friedman had predicted.
So, this gave birth to the hunt for the Hubble parameter, the value that tells us how fast the universe is expanding at the moment, and the so-called deceleration parameter, that measures how this expansion rate is changing over time.
Yes, exactly. The realization of the hot Big Bang's role in the early stages of our universe meant understanding the expansion of the universe as a kind of race. The initial expansion rate strived to push everything apart, while the gravitational effects of all the matter and energy in the universe strive to pull everything back together.
So, the universe's expansion is like a cosmic tug-of-war between the initial explosion and gravity. That's quite a fascinating way to perceive it.
As we understand it, the relationship between the initial expansion rate and the amount of matter and radiation in the universe governs its ultimate fate. There are three primary scenarios.
Each scenario is like a cosmic story, isn't it?
Exactly. In the first scenario, if there is more matter and radiation than expansion, the universe expands for a while, but gravity slows down this expansion. Eventually, gravity overcomes this expansion, causing everything to recollapse, ending with a big crunch.
That sounds dramatic. But what if there is less matter and radiation than expansion?
In that scenario, the universe continues to expand indefinitely. Although gravity slows it down, it never entirely stops. This results in a big freeze fate.
So it's either a big crunch or a big freeze. What's the third scenario?
This one's interesting. If there's exactly enough matter and radiation to balance the initial expansion, the universe slows down but never stops. It's like coasting forever on the edge. If there were just one more atom, it would collapse.
So, it's a fine balance. But none of these scenarios are what we observe, right?
Correct. Surprisingly, none of these scenarios match the data. Instead, we found that the universe isn't decelerating but is accelerating instead. This discovery threw us for a loop and brought forth the term dark energy.
Dark energy. That sounds mysterious. So, despite the gravity trying to pull everything back, something is driving the universe to expand at an ever-increasing rate?
Yes, it's truly one of the great mysteries in our understanding of the universe. The slowing down of a distant galaxy's recession would have guided us to understand which scenario described our universe, and hence infer its fate and composition. But observations showed an interesting pattern.
A pattern? What do you mean?
Well, a distant galaxy's recession would have started off fast, then slowed down for a while, and about 6 billion years ago, it stopped slowing down and started speeding up.
So, it's like the universe hit the gas pedal after slowing down.
That's one way to put it. This acceleration was a surprise. We had thought the universe was behaving like a car slowing down after a start, with everything within the universe gravitationally pulling it back together.
And this was because we assumed that everything in the universe behaved like matter and radiation, right?
Correct. We accounted for normal matter, black holes, all forms of light, gravitational waves, neutrinos, and even dark matter. But we overlooked the possibility of an exotic form of energy.
Exotic form of energy? That sounds intriguing.
Indeed, it's a form of energy that doesn't get less dense as the universe expands. There could be energy inherent to the fabric of space itself. This could possibly arise from Einstein's cosmological constant or from the zero-point energy of the quantum vacuum.
So, Einstein's theory and quantum physics both suggest a form of energy that could be accelerating the universe. That's truly mind-boggling.
Yes, it's one of the frontiers of cosmology. Trying to understand this dark energy is one of the great challenges we face today.
This discussion reminds me of a childhood memory. When I was a kid, I had a little toy car that was powered by a spring. I would wind it up, and it would zoom across the floor, gradually slowing down until it eventually stopped. But imagine if, instead of slowing down, the car actually started speeding up the farther it went.
That's an apt analogy for what we're discussing. But of course, in the case of the universe, we're dealing with something far more mysterious than a spring-loaded mechanism. We're talking about a potential energy inherent to the fabric of space itself.
True, it's far more complex. But my little toy car memory helps me grasp this idea of acceleration after an initial expansion. It's as if the universe has its own hidden, cosmic spring that's pushing it to expand faster and faster.
That's a fascinating way to think about it, and a great example of how sometimes understanding complex concepts can start with simple, relatable experiences. Now, let's dive a bit deeper into the implications of this acceleration.
I'm all ears. This is like unwinding the spring of the universe and observing its cosmic journey.
Nicely put. The important thing to clarify is that while the expansion itself is accelerating, the expansion rate is not. It has been decreasing since the early stages, and it's continuing to do so. It's just that its final value won't be zero, but a positive, greater than zero value.
So, it's like the universe is decelerating at a decreasing rate?
Precisely. And that's the twist that dark energy brings to our understanding of the universe's expansion. Here's a fascinating twist. The recession speed that you measure for any individual object within the expanding universe is accelerating. Let's say a distant galaxy today is located about 1 billion light-years away. It's receding at around 21,000 kilometers per second. But in the future, as it moves further away, it will be receding at a faster rate.
That's like throwing a ball, and instead of it slowing down and falling, it accelerates and speeds up in midair.
Yes, exactly. And there's a limit to how far we can reach. As objects get pushed to greater distances, their recession speed will appear to increase, even surpassing the speed of light at some point. Once that occurs, no signal or message that we send can ever reach that destination.
This reminds me of when I used to race paper boats with my friends in the monsoon rains. We would place our little paper boats on the edge of a puddle, and as the water level rose, the boats would drift away. The further they went, the faster they seemed to move, until eventually, they were out of sight.
That's a beautiful analogy. And it's also a bit melancholic when you think about it in the context of the universe.
True, but then again, it also makes the cosmic story all the more intriguing. So, what's ultimately driving the expansion of the universe?
That's the million-dollar question. And we're still trying to fully answer it. But, as we've been discussing, dark energy appears to be a significant factor. So, there are two main factors responsible for the expansion of the universe: the initial expansion and the onset of dark energy. Interestingly, these two factors might be related.
Wait, so the initial expansion wasn't caused by the Big Bang?
Actually, the initial expansion comes from the end of cosmic inflation, a period that preceded and set up the hot Big Bang. During inflation, the universe expanded at a constant rate due to a large amount of energy inherent to space.
I see. And where did this energy come from?
When inflation ended, almost all of this energy transformed into matter and radiation. The energy density at that time determined the expansion rate of the universe.
So, that's how the universe started expanding so rapidly. But what about dark energy?
Dark energy is different. As the universe expands, the matter and radiation densities drop, but the dark energy density remains constant.
So as the universe gets larger, dark energy becomes a dominant force in its expansion?
Exactly. It might be incredibly small, but it's persistent. As new space is created, the density of dark energy stays constant, which eventually leads it to dominate the expansion of the universe. So, after billions of years, here we are, in a universe that is dominated by dark energy. It's this dark energy that's now responsible for driving the expansion of the universe.
And you mentioned earlier that there's a possibility that the early period of inflation and the current period of dark energy domination might be related?
Yes, it's a tantalizing possibility. It's speculative, but it offers an interesting avenue for exploration.
But we still don't know how or why these things exist, right?
Correct. We observe their effects, but the underlying explanations still elude us. However, the search for those answers is what makes this journey so exciting.
Maybe one of our listeners will be the one to find those answers.
I wouldn't be surprised. The quest for knowledge is a continuous journey, and everyone is invited to take part. Who knows? The next big discovery in understanding our universe could come from anywhere or anyone. Well, there we have it, folks. The expansion of the universe is a captivating riddle, stretching back to the early 20th century, and it still isn't fully solved. It seems, despite our advancements, the cosmos is still keeping some of its secrets, such as the relationship between the initial cosmic inflation and the dark energy that dominates our universe today. But hey, isn't that the beauty of it all? The more we uncover, the more there is to discover.
Absolutely, and who knows? Maybe one of our listeners will be the next great mind to unravel these cosmic mysteries. So, if you enjoyed this episode, don't forget to hit that like button, leave us a comment with your thoughts, and share this episode with your friends. Let's spread the wonder and fascination of our amazing universe.
Couldn't have said it better myself. Thank you all for tuning in. We appreciate your support and curiosity.
And remember, no matter how much we learn, there's always more out there to discover. Stay curious, friends. Cesar and Sonia Guimaraes, goodbye.
This fascinating journey into the expansion of the universe was guided by an article titled Ask Ethan, What Drives the Expansion of the Universe, by Ethan Siegel, published on Big Think on November 3, 2023. The full URL is in the video description if you want to delve deeper into the subject. Now, it's time for me to sign off. Catch you on the next episode.